Okay, so okay, so let us restart our sections of talks here in the Bingo collaboration meeting. So the first talk of this afternoon is from Eduardo Mericia, from INPE. So Eduardo, thank you so much for accepting our invitation, and feel free to start your talk.
Thank you very much, João. I will share my screen. Are you seeing my screen, full screen?
Yes, we can see.
Okay, thank you. So I will present intensity mapping pipeline for Bingo vision simulations and data analysis, current status and capabilities. So this is the INPE team working on this. And 1 minute, I have to change the things on my screen here. Okay, so as input to the pipeline, we used some information from Fiducial Bingo. So we use as input a site coordinates, for example, a focal length, and a number of horns, central declination, and the system temperature. But in our simulations, we simulate with different system temperatures. We work with 30 channels, 30 frequency channels, and a sampling time different from this I will show later, and a beam resolution at a central frequency of the band frequency of 40 arcminutes. So the horn arrangement that we used is a double rectangular. We're using 28 horns placed in this shape with 4 columns of containing 7 horns. And on the right, we have the dot file that we use as input. And we inform here the system temperature, the X and Y offsets on the focal plane, and the K factor used in the geometry equation. So here we have a full block diagram for this pipeline. We don't have all these modules working now, but we have part of them. For example, we have input as input. We can use we can produce H1 maps from an internal model, or we can read maps, the H1 maps generated with external models. So the first radio burst we can't read yet. The foregrounds we can produce as the same thing to the H1 map. The foregrounds, the astrophysical foregrounds, we can generate them with the internal models, or we can read them for external models. For example, PSM. We have a model of a FI model that is not working full yet, but we are working on this, and we have the atmosphere working now. And the information about the instrument, we have the instrument specification, instrument noise, and I will speak more about this in next slides. And then we can produce the time order data, and we don't have this step, the flex for transients and the time order data cleaning, but we have a map making, a naive map making method working, and we are working on work to integrate other map making methods in this step. And then we can produce the multi-frequency maps and pass to the foreground removal step, the bottom here. The foreground removal here, we can we have some methods integrated to the pipeline, and we have to add a debiasing procedure to recover the H1 sign-on. And the other models we don't have integrated yet, but we have some people working on this. So our simulations were maybe using some parameters as observation time of 5 days, a sampling time of 1 second, different of the fiducial window. We produce a quick simulation. Here we produce a number of samples per horn per channel equal to 1,200 samples, the measurements. Then side that we use is 256. The system temperature, we change this system temperature varying from 50 Kelvin, 60 Kelvin, 70 Kelvin. As I said, the astrophysical foregrounds, we included his synchrotron free extragalactic faint radio point sources, the H1, the target signal. We tested 2 component separation methods, PCA and GNU. And our simulations were divided in 5 sequences to show the capabilities of the pipeline. So the 0 sequences, we included only thermal noise. So the thermal noise produced from the radiometry equation. So the system temperature and depends on the standard deviation depends on the system temperature, the time of each pixel is observed, and the width of the channel, the frequency channel. So here we have the TODs for different system temperatures. We can see an increase in the amplitude of the noise here. The histograms, I will pass quickly here because it's only to informative results. So you can we produce the histograms and the PSDs for the 3 cases, and the last we have the angular power spectrum for the thermal noise. So in sequence 1, we included one more component, the 1/f noise. The 1/f noise is modeled in the pipeline using this power spectrum density. Is depending on the this power spectrum density contains the power of the thermal noise and the 1/f, the first term and the second term. The second term related to the 1/f, we have a temporal correlation. Is this alpha index, and the fk is the new frequency. The frequency when the frequency at the thermal noise is equal to the in terms of the power spectrum density, the thermal noise is equal to 1/f noise at this frequency. And we have this term related to the frequency channel correlations. So we use the different system temperatures, the Lie frequency for this 1 millihertz, the temporal correlation alpha equal 1, the 1/f here, and the frequency correlation beta equals 0. So we consider here in this sequence only the correlated, totally correlated, the frequency correlations, the noise is totally correlated with frequency. So here we have we use the cosine filter here with a filter scale 360 seconds. So this equation, the right equation, we can see the definition of the cosine filter. And at FC, the signal is reduced to the half. So we have the time series here. On the left, we have with no filter, and the right you have with the defined filter. The histograms, the PSDs, it is an important part of the simulation, because we can see here on the left the signal with no filter. We can see a decreasing in the component, the 1/f component is decreasing here. And at the right, when we apply the filter scale, we can remove this long duration, how can I say this? We remove this components with the long periods, long-term fluctuations. So we can remove this filter. The maps we can see here. When we have no filter, we can see some structures related to this long duration fluctuations of the noise. So you can see some structures in the maps. But when we plot the maps produced with the filter, we can't see these fluctuations. These large structures can't see anymore in these maps. So the component separation step in the sequence one, we use the PCA method. So we apply the PCA to the observation maps, and we can see here that the PCA removes part of the 1/f. In red, we can see the 1/f noise. In green, we can see the thermal noise. So PCA 1 mode in black dashed, and the PCA 2 modes in yellow dashed. So you can see that the PCA is able to remove the 1/f to keep the thermal noise in this case. So we can pass through the sequence 2 when we have age 1 plus thermal noise. There's the components. The age 1 model that we used are based on a theoretical model. We can generate realizations of age 1 from angular power spectrum of this component. So in this case, we use only the internal model, but we can read the external, like for example, Flask, the maps produced with Flask. And then we have the same thing, the histogram, COD, PSDs, the maps where you can see some the maps, the observation, the observed maps contain H1 plus thermal noise, and the bottom we have a observed H1 map, our target signal here. And the angular power spectrum, you have an interesting when we apply the PCA. So the H1 is in red, so we can apply to the PCA to the H1 plus thermal noise signal, and we can't remove the thermal noise. So the PCA keeps the H1 plus thermal noise. You can see in the three angular three frames, you can see the same thing. So as a clue to that we have to try to recover the H1 plus thermal noise and then apply another methodology to recover the H1 sign. So in sequence 3, we included the three previous components: H1 thermal noise, 1/f noise, simulated with different knee frequencies, and we expect that a higher knee frequency is more difficult to remove the 1/f. We test different frequency correlations too, and going from this value 1 to 10 to the minus 5, in, representing the 0, because to avoid a numerical error, and we can increase. So a higher frequency correlations turns the component separation step capable to remove the 1/f. So and then we test to the with no filter and with Cosine filter. So you have the TODs for different system temperatures, and consider no filter and filter scale here, and then we keep the system temperature and varying the knee frequency in this case, and with no filter and with filter, and we tested to the different frequency correlations here, but we can see difference here yet. The histograms, the PSGs, the PSGs here we can see that all the PSGs is not producing, the signal is not filtered. So you can see the increase of the knee frequency. You can see this inclination of the PSG is higher. And then when we apply the filter, we remove the power of the sign at these time scales. You can see the same. So the maps here, the same thing here with no filter. We have some structures related to the 1/f, and when we apply the filter, we remove these structures, removes part of the 1/f. The maps here, in a different case, considering a higher knee frequency. And then we have the angular power spectrum. So on the left, we have in the case our system temperature is equal to 70 Kelvin, and we have a knee frequency, the low knee frequency, and no filter. In this case, the signal, the observation is in red, and we apply the PCA. We have this black and blue curves, and the green is the H1 plus thermal noise. So when we increase the beta, the frequency correlation, the frequency uncorrelation, when we increase the frequency uncorrelation, it's more difficult to the PCA to remove the 1/f, and we can see here when beta equals 0.5, we have almost all the 1/f is preserved. And in this case, on the right, when we apply the filter scale, is the red curve is H1 plus thermal noise, and in red we have the observation. So the green curve is we not consider the filter here, and the red curve we have the observation filter, and we apply the PCA method. We have a difficult to remove the remain 1/f. When we increase the knee frequency to 0.1 hertz, we have a more difficult case, because you can see the power of the signal is higher at more time scales, and we can see that the filter removers part of the filter is able to remove part of the 1/f, but not all the power, the high power of the 1/f. And the last sequence, we simulated all the components that we have now. So the H1, the galactic, the astrophysical foregrounds, the thermal noise, and the 1/f. And we tested two different frequencies again, and we fixed to the frequency correlation to 0.25, and we performed the component separation with PCA and now with GNU. So here we have the synchrotron model, the full sky, and when we apply the observation, the observation. So here we have a problem in the pointing model. We are working on this to fix this, but these results are produced only in these dislocated stripes here. And we have the faint point source, the observed faint point source. And then we have the maps, so the observation maps, the top, and we apply the PCA 3 modes and other modes until the 11 modes, and we compare with GNU here. The reconstructed H1 plus thermal noise map with GNU, and we can compare the input H1 plus thermal noise. In both cases here with no filter and with filter. And again, now using a higher knee frequency. And the angular power spectra here, we have the observation in red, but black, we have change this. In black, we have PCA 3 modes, and we apply the PCA 11 modes. We can see here that the reconstructed angular power spectra is near to the H1 plus thermal noise. And in gray, we can see the GNU reconstructed H1 plus thermal noise signal, but we had to consider here that with GNUC we can estimate this bias that we have here using a higher number of realizations of thermal noise and the theoretical H1 signal, and we can estimate this bias and reconstruct the H1. So with GNUC we can go further here in this step, and we will test this in the next steps. So when we increase the NIF frequency, we have more difficult to remove the foregrounds. You can see on the right, and we apply the filter. We have different situations now, because we have a PCA 3 modes, 4 modes, and 5 modes here. And 5 modes is approximating to the filtered signal, and the green one is a unfiltered signal. So we can see this difference here because we are losing part of the signal here because the filter, and the same thing on the right. So the next steps are first fix the pointing and verify models to simulate again these sequences. Simulate with H1 maps generated with external models. Simulate with foregrounds generated with external models, applying the debiasing method to GNUC. Output the signal, the output signal from GNUC to recover the H1, and integrate this debiasing method to the pipeline to compare the input and output. Optimize the long time scalar signal filter, because we are using a default filter time scale, so we can change this and test until to trying to optimize. We intend to integrate other map making methods like the striper and maximum likelihood. Perform component separation with other methods that are available but not integrated to the pipeline. We intend to work to read the real beam measurements to include on the simulations. We have to define a way to quantify the difference between the input-output maps, the H1 maps, the input and the output H1 maps, and our main goal is to identify what issues can impact the recovery of the H1 sign. Which are our main problems in this procedure. So some acknowledgements. The developers of the pipeline here, and the institutions, and the BEAGLE, CNPq, INPE, and BEAGLE collaboration. Thank you very much.
Okay, thank you, Eduardo. So we can have time for questions, comments, question and comment. Oh. Okay, so then we can proceed for our next speaker, which is going to be Professor Jair Zan. I'm just going to open the file here in computer. This one, yeah. Share here.
Okay, for the online audience, can you see the screen perfectly?
Are you listening to us? Can you see the screen, please?
Yeah, we can see on YouTube.
Yes.
All right, so can you give me the mouse? Or whatever.
Yeah, can you?
Oh, okay.
Okay, keep it free.
Okay, thanks for the opportunity, and I'm really happy to be here in Brazil. It's my first time again. And today I will talk about the Bingo pipeline for 21st technology and the current progress and challenge on behalf of the stage 2 and 3 groups that are in charge of this progress. So that's basically on the question I would like to answer and try to give you an information about what these kind of things are doing. So what is Wingo doing? And well, should say what will Wingo do not really do. And something that about the data compressing and also what the radio signals really comes from. What the compose of the radio signals that we would like to receive. And next is what the pipeline will do. And finally, some of the research topics. So here, first give you an impression of our geographic location here. And let me just try to emphasize this point that you can see if we block this point, we will miss a big part of the Earth. So our location is very important to cover the whole side. And so this is the site itself. It's an image that we have seen for quite some time. But you can see here, let me just start from the very hardware part that you can really look at those things. We have some house, some power plants, and in this figure over there, that is the first one, right? So exactly speaking, what is going on over there? Let's just give a very simple explanation. So let's see, here is the artist view. And for the horns, they are the feed, or they are just receiving the signals. And you already have a look at the workflow. So the workflow is the very tiny version of what things we're doing. We just connect very little cables out of this end and send this data to a receiver. And this receiver is the receiver that currently in Shanghai Observatory we have. I just take it as an example. It's not the real things that we are using now for it. So you can see these are the cables that plug into this black box, and you know what's going on in the black box. And finally, you get something out from here. From here, this is just the fiber cable that you can directly connect to your computer. So you get some signal from here. So what's exactly doing in this black box? You only need to know is that what's coming in here is the voltage or the electromagnetic waves that you really receive from the sky, whatever they come from. Okay. So you have those voltage numbers, and you need to amplify the signals themselves because they are very tiny signals. And you need to amplify those and digitize those into numbers. First, they are not really numbers. You need to get those into numbers. And then you do a channelization so that you know at which frequency what is the power, and also calculate the power spectrum. So now finally you have the data set that tells you that at each different frequency what is the power you're getting. Okay. So then this thing will go through into the data center, or you get it into a computer. Okay, you get it into the computer. Then what the computer will need to do, currently we would like to separate the pipeline into two parts. One part is that to really detect FRBs, and another part is to integrate over time and get the one, then we're going to get the mapping signals. We to do that is really need to save some hard disks because let's think about an easy number, not too hard, but an easy number. For example, if we send in the data at a rate about 1 gigabyte per second, then over a year we want to take data. Over a year, how many data that is? We just count some very simple numbers. We find the number will be about 100 petabytes. 100 petabytes itself is too expensive to store all of those, right? So usually we really need to pick out those data. So one part is that with some of the transients we are more interested to look at. So we need to take those out, like the FRBs we are interested to look at. So take those out. But FRB only lasts for a very short time. So you only take those very short time data out, and the others are not useful. You just throw them away. So by doing this, you can save some space, but that's this part is not what we are interested in our group what are doing. And so we should follow this line. Yeah, we need to integrate over time because we first when we take data, we take the data at every several microseconds. But in fact, we can integrate them by over time. For example, we take data every second. Then it will save you quite a lot of space. You don't need to take many numbers. So in this way, then we inject it here. So exactly that's here is the pipeline that you need to go through to find the 21 centimeter sequence. So let me tell you about the research topics currently in the stages currently we are doing. We are doing like an end-to-end simulation, like map making, program removal, cross-correlating, blah blah blah. These things. But let me just put them into these pipelines that I showed you. So here, this part will have the baseline, the themes, alphas. These are the things that when you observe, you really have. Okay, and we need to go through this whole thing to get the maps of things that Eduardo just told you. Then we need to do a component separation, and then we find the power spectrum or like a light spectrum that like Giovanni is doing. And then you need to measure the VAOs or the cosmological parameters. And for the input, we need to understand what is going into the signal. What is the signal really composed of? So we need to know what the signal composed of. One of the things we need to get is the 21 centimeter signal and many other things. So we need to pick up 21 centimeter signal. So that's the whole process. So here is the topics that currently we are covering. The topics we are covering, you can see that these are the research topics I just already listed over there. You don't need to really understand what I'm doing. But when we put it here, so the remapping and end-to-end simulation, they are mostly this part to simulate the signal and what kind of signal we will do, what we will see in this part. And for this part, it's mostly about the raw data themselves. We need to know how to calibrate them, how to get those numbers into physical units. How do we get those considered about the instrumental effects? We need to remove many of those. And for that part, we need to remove RFI. RFI is the radio frequency interference that's usually caused by human beings ourselves. We need to remove those parts. And then the map making works in this block. Okay, we need to make some of the maps. So you receive data and you know where the data comes from the sky. So you put the number at those sky. At different location of the sky, a different number. When you put many numbers together, you will have that's map making. And then you need to do a foreground removal. So you remove the part that you're not interested, you only left over 21 centimeter signal you want to have. And then further, you want to calculate like the power spectrums. We want to calculate. Currently, we are doing like cross correlations of high spectrums. That is things we want to see. And finally, we want to identify the VAO signals. That's one of the key goals, and it's written in our name. Our name is Baronic oscillation. So that's in our name. We need to look at and also get the cosmological activities. That we need to know the cosmological parameters we are interested. Okay, so that's basically the whole thing. You can see the dashed boxes is something we are not doing. Or we currently do not really know what to do, and the solid boxes is already doing, some of those are already done. So let's think about what the radio signals really composed of when you receive something by the telescope. Or you don't really need a telescope, you just put an antenna over there, and you want to receive some of the radio signals, what they are composed of. So we have something like, for example, the cosmic microwave background itself, and it's a thermal background. So I list it as thermal. This is the rate of the expansion of the universe itself. And then we have some extragalactic radio sources. Those radio sources usually are very far away from us, and if you don't have very good resolution, when you look at those, they just look like a point. A point that's very shiny over there. Okay? And usually they are non-thermal by their emission. So they have special emission spectrums themselves. And but usually they are smooth. They're smooth because they emit the radiation themselves. In the physics mechanism that, for example, synchrotron radiation, those electrons moving in the magnetic field and they give you some signals. And also then we have the Milky Way emissions. The Milky Way emissions, that's the emission from our own Milky Way. Our own Milky Way have magnetic field, have electrons, and so they always give you some signals. And then you have the 21 centimeter signal, that's what we are really curious about. So they come from the neutral hydrogens themselves. And neutral hydrogens also are everywhere in the universe. And so when they emit the 21 centimeter signal, we capture those, we will try to know what is going on in the distribution of the gas. And then we also have the atmosphere or the ground themselves. You know, even atmosphere or the ground themselves are thermal bodies. They're also radiant. Okay? So they will also provide you some signals. And the solar system of objects, for example, you do not directly look at the sun, because the sun itself is very bright. So it also gives you some signals. And RFIs themselves are the things that we hold every day, and also some other instrumental noises. So it's composed of many things. They're quite complicated. And so by going through the whole thing, we need to first just simulate everything we know and put them together and see if we can get the signals out. For example, this is one example of the 21 centimeter map I generated. And you can see here are certifications. They look very beautiful. They represent the large structure of the universe themselves. So this is something you want to see. But in reality, it's not look like this. And so besides this kind of map, you generate one, but this one only represents for one cosmology or one set of cosmological parameters. What if you have many, you want to see what happens if we have different cosmology, we have different cosmological parameters, what will happen? So then there is a technique called remapping, means that starting from one simulation set, we can, from this simulation set, using this technique, we can move the particles or move payloads from one position to another so that they will represent the new position in a new cosmological parameter space. So that's the way that you can survey around the cosmological parameter space. So we have, these are the parameters, these are the power spectrums we measured. So here are two lines you can see is the red line is the original, or you can say this is a simulation, and the black line is we start from another simulation and map those into the new one. And you can see these two systems. And then we also need to do component separation. Component separation means we want to separate many components. And what are the components? The components are, for example, CMB, free emission, signature emission, FRPS, and 21 centimeter signal, manual of those. Right? You want to separate them out. But the difficulty we have already discussed today many times, that the difficulty is that the 21 centimeter signal itself is only 1 over 10,000, somehow like that, over the other things. Well, fortunately, if we look at when we look at these different mass at different frequencies, they behave differently. So that will help us to differ them apart. And then we also need to simulate how the telescope itself observe the sky. They point at the sky different times. They point at different directions. So when we go through the sky, they will hit over the sky many different times. So every different time you receive a data. The data means it comes from a specific location. So that this process is called hiding. So you put in the simulations and hide it, and you imagine it as a telescope. So this process called hide, and already presented by our sample. So when you hit over the sky, this is the so-called heat map. So that means you have those different pointing spaces in the sky map, and you are just getting data from these kind of positions. So comparing the original sky map, this is the original one, and compared to the finally you make the map, we find they are similar. They must be similar, otherwise this map is generated by Travel job. And then we need to separate the component apart. So different components actually they have different physical background, so they have different behavior. What kind of behavior? So this part of work was mainly done by Eduardo and Alessandro. You can see that this is the whole ground. We already put in 21 centimeter signal, but it doesn't really look like the 21 centimeter map you have seen in the application, because the foreground itself is very strong, especially the Milky Way itself. Okay, so we need to mask them out, and also we also have the bingo coverage itself. We are just scanning over the sky at this band. So also take this part out, because this part is too bright as the galaxy itself. So finally we have this kind of thing. So then when you go through this map at different frequencies, for example, at different frequencies, different components behave differently. For example, these components coming from the Milky Way, the secondary emission or frequent emission, they are the major contamination we want to remove. They are smooth over different frequencies because they're coming from the same object. Right? They come from the same object. They come from our own galaxy, or they come from other galaxies. They always come from the same object. So at different frequencies, they also look very similar. But if you look at the 21 centimeter signal themselves, they fluctuate a lot, because at different frequencies, you are looking at different objects. You are looking at different vectors, so they look very different. So then the key here is to try to find some algorithm to help you pick out these things that look very similar at a different frequency, and left over only these things look very different. So yeah, we will apply these different kind of algorithms like fast ICH, MCA, or Junior, and they all work. And they will just give you the power spectrum you can see here. So we can see here the input one is the black line, and the green line or the red line are the things that you already reconstruct. And so next is we can not only do the auto power spectrum. So when we talk about this kind of power spectrums, you can look at this number, this tiny number here. CL, the unit is mu Kelvin square, means that it's actually the correlation between the map itself. So when we have one map, we want to correlate with itself. So that's the auto correlation we want to do. That is representing only the signal of 21 centimeter itself. But 21 centimeter is very weak, so we want to have some other maps that can cross correlate with this map, so that you can get the signal noise ratio higher. Usually what we do, we use other band, we use other observations, for example, optical observations. We found a galaxy, and the galaxy itself not only emits 21 centimeter signal you want to see, but also emits light. It emits the optical themselves, so the galaxies themselves are bright. So you correlate themselves, because they're coming from the same object, they must have a good correlation. So that's the cross correlation if you do. That's the pipeline of the cross correlation. You need to go to many details here. The only thing you know is that from a single simulation, if we have a simulation, one part we want to know the 21 centimeter emission, and another part we want to know the optical emission and the cross correlation. That's all. And that's the total cross correlation of these two maps. So that this page is provided by Bruno. And so here is the very first slide. For example, let's imagine we have an observation of bingo and the wiggle Z. We put a cross correlation over them, we will have some signal, right? So that's a very basic story. And another cross correlation we are also doing currently is by like simple Gabriel Chokso. And here is the doing that we know this part is the coverage of LNST. It's a optical telescope under construction. And this part is the coverage of bingo. So we have a very good overlap, right? When we have a good overlap, we want to see what kind of cross correlation they will have. And they will have cross correlations, and it will also tell us some more information. This is the full sky that we currently make some simulations. We simulate on this side, we simulate the 21 centimeter map, and on this side we simulate the optical galaxies. And you need to cross refer these two maps. They look similar. They must look similar. They have some correlations. And then, in order to really get the final cosmological inference itself, we also need to know what is error bars. So you get some data, and you find that every data itself has an error bar. Where the error bar really comes from? Well, the error bar itself needs us to do many times of simulations and see what is the error. Every time different realization to give you different signal, you need the error. So one way to do so is that we need to run many simulations. The simulations themselves are expensive, so we run so-called fast simulation. So this is the so-called particular simulation in this way. So because this thing is cheap, so we can run, for example, 100 times. So you get 100 different universe, and when you average over 100 different universe, you have an average value. You also have an error bar. So here is the box itself inside, and we need to replicate it many times so that you can have a coverage like this. Now, if you have a coverage like this, you will select the bingo band, the bingo mask, and then calculate their power spectrum and calculate the covariance matrix there. So this is the covariance matrix you can use from. This done by and Zheng Hao also in my Institute of Shanghai Astronomy Observatory. For this maps, you can even also get the data from our. And then after you have done this, we have the signal. We have many different universe, the 21 centimeter signals. Then we want to put in the white noise, and also put in the foreground and remove the foreground. When you remove foreground, you have some residues. They will also just provide you just like a noise. So you have a signal plus some noise, put them together, and you finally want to get the cosmological parameters from it. And this part of work done by Pablo will also give you a very detailed presentation. And from Pablo, we also use other methods to generate many times of the signal itself to give you calculate the covariance matrix. We have calculated the covariance matrix, so give you the error bars for the data and fit to the sporadic curves. Then you want the best fitting values. The best fitting values are the cosmological inference. So then Pablo will give you these contours. And also the best fit curves, and compared to the data points, they're fit pretty well. That's exactly what we want. And beside that, we have the cosmological inference. We also want to exactly detect the BAO signals. The BAO signals are simply those wiggles where you want to see in the power spectrum. And you can see those wiggles and just pick those wiggles out. Not the whole thing of the power spectrum. You can pick them out. By picking them out, you need to also construct a model that have those wiggles. And you fix your wiggles with those ones data, and you find where are the wiggles. And they will just provide the information where actually the wiggles are, and they are telling you that the size of those circles. So when we calculate, for example, the angular power spectrum or autocorrelation functions, alpha parameter, don't worry. Alpha parameter, if it equals to 1, means that your fitting wiggles are exactly at the point of the data. If it's 0.8, it's to the left. If 1.8, 1.2 is to the right. So this region apart means you detected the BAO wiggle. So in fact, we can really successfully detect the BAO wiggles, and we have those signals. And what's missing? What's missing? I put a figure here. I got it from a website here called iPath. It's a pipeline that was done for the H1 survey from FAST telescope. You already know about FAST anymore. And you can see here this map usually will call it waterfall. Is that in the x-axis you have the frequency, and in the y-axis you have the time. Remember that in the x-axis you have frequency, and every different frequency with a power. That's what exactly we measure from the telescope. You have a power, and then different power give you different colors, and through time you form the y-axis, so you can see something. For example, you can see a line here. This line is very bright, and this frequency is very bright, and it's always there. And this part is alpha. So it's an inference from some artificial things. You need to mask them out. So this white bar means mask them out. You also have something else working like this. You also want to mask them out. You also have these kind of wiggles at the different frequencies. That's also something we need to fit and mask them out. And here we also have a line here. You see, also have a line, right? And look at the frequency of this line. It's at 1420. So that's the 21 centimeter signal. So it's not alpha. You do not mask them out and pick it up. So you mask this part out. This is alpha, and this part is what we need. And when you are making using this kind of data, you will just find an object in the list. That's called an object, emitting 21 centimeters. So, but this part of masking these RFIs and fitting with these background things, we're not doing it yet. Okay, so this part, say, is missing. This part also missing. It's well, it's not really a problem because these kind of things are different for different telescopes. So we only after really constructing the whole telescope, we can have a better understanding and try to remove those all. Before that, we can simulate something, but that's just a preparation for our own software. Okay. So I would like to say that because we have these kind of solid boxes here, so I can say that for the 21 centimeter quantity itself, we're ready for doing that. But I really works them though. So we need to get the telescope done. And then need to get this out and finally can go through this. Okay, so that's my thought. Thanks.
Okay, do you have any questions, any comments? You can speak. Podem falar daí, só falar pouco alto que a câmera pega.
How far do you think we can measure PAO?
How far
In 5 years?
in 5 years? Let me think. I think the easiest person to measure PAO is doing the cross correlation. And for doing cross correlation, I think after building the telescope and get the data right, about 1 year later, should be okay.
Very good.
Yes, I would say optimistic.
Of the
Is it
calibration.
realistic? It's just optimistic or realistic?
Well, actually, realistic, but you mean, I mean, there is some typos. Get every noise done, especially this part and this part. Get all this part done. We'll get it. Because the one really good thing about Vigo itself is it's a dedicated telescope. So over 1 year, we will have integration time about 5,000 hours.
But in 1 year, we don't have the night quiz, no? We have to move the phones a little bit in order to have a better observation opportunity.
The a bit better homogeneity over time. It's just that it's sky coverage itself. The other guys, when they have a much smaller sky coverage, already detected the cross-correlated signal. I believe more.
For the calibration, could we use, for instance, the local hydrogen line? Because the local hydrogen is about that 120.
You mean this one?
Yes.
Uh, calibration, they are very, calibration, we always use the word, but in different environment, it means different things. So, maybe we should talk in the details later.
Okay, so let's thank Jae-Yoon again. Thank you. So now for the last talk, we're going to have a presentation of Giordani. I'm just going to set here. Legal, legal. Só colocar aqui. Maybe, sorry.
Everyone can see the slides. Online presentation.
Let me see. Yes, we have seen them. Okay. Okay, so thank you, Giordani. Please start your presentations.
Okay, thank you for the invitation. For the legal collaboration meeting. So I am Giordani Vieira from USP, São Paulo. I am a student of Professor, supervised by Professor Vidal. And I'll talk about the Bispectrum project and legal regulatory. Okay, my outline is talk with of you about the what's the bispec? It's the you some say something about what's the bispec, but I will talk a little bit more because I work in different way from the professor's son. They talk with the theory. I thought I work with the simulation, with the observations.
So I will explain how we calculate the bispectrum from this maps and simulation. After this, I will say about the why we study the bispectrum, why we need to understand the bispectrum. I'll talk about our model to calculate the bispectrum, how we construct the model. Okay, how equation we use and how equation we calculate with the computers to understand and make the calculations about the bispectrum. I will talk about the bispectrum case. We work with 3 cases of the bispectrum. The professor is saying about the case, the squeeze, the local case. I will talk about the 3 cases we use in our work. Then I will show you some results and talk about the next steps to do this work. Okay, so first, what's the bispectrum? So the bispectrum is the pre-order of the angular endpoint and going to find power step. So it's like to study the one step more than the variance of the statistical. Okay, if you have a field theory, when we will go to the asymmetry of the distribution, we study the bispectrum of the distribution. Okay, we study the 3-point function of this distribution. In our case, our field theory is the image of the sky, or in this case, the simulation of the sky. So, for instance, I will show here. We have 3 dots in the sky, and we need to study the correlation between the 3 points. It's the how I talk about the study bispectrum. This is study bispectrum. There are 3 points in the field, and study the correlation between the 3 points. For instance, we see this. So, why study the bispectrum? So, the bispectrum is the non-Gaussianity of the distribution. And in this case, we use the bispectrum to study the non-Gaussians in 20 fields associated in this case with the inflationary period. But it's not for study this, but we can study the fluctuations in the boundary power spectrum, or we can study the interactions between the dark energy and dark matter in big multiples, right? And in our case, we start to study this. There's points here, but we know a new use for the bispectrum or product. We study the foreground residuals when we make the foreground removes from the maps, as we call as we say about using the paper file. When we take out the foregrounds from the sky maps, get only the 21 centimeters, we need to know if the foreground still make a difference in our 21 centimeter simulation. And we use this idea to study the bispectrum in this case. We make this with the paper file, and we will make this again with the more improved model, because we improve this code. So, about the bispectrum model, I will talk about the mathematics a little bit here. How do we calculate the bispectrum? So, in our case, we calculate using harmonic spherical transformation. But the bispectrum is basically the integral over 3 maps of simulation, because we need to see 3 dots, 3 points in the sky. So I don't get to the same map and look at 3 points. I can get 3 same maps and look at different points in these maps, but overlap 3 maps. So I can look at different maps for different purposes. It's good to choose the correlation between the 3 points in different brackets. It's like the cross correlation. Then we can make this with this code. We get the bispectral from sky maps. We made their multiple spherical transformation maps to study with the null functions. And we have the ALMs of this harmonic spherical transformations, and then we need to calculate this integral here, the gap integral. It's in the previous words in the paper 5, for example, for instance. It's a big problem because it's hard to calculate this integral. And so we made some changes in our code to do this more easily and quickly. Then to calculate the bispectrum total, we need to use this last equation. Basically, a bigger 3J symbols and normalization here and the ALMs. So, okay, the Gaussian integral is a problem. How we work to turn around this problem, to take away, to cut this problem? We use the recursion technique. We get the recursion equation for the big vector 3J symbol and use a matrix relation to calculate more easily these values, the values of the big vector 3J. We have a matrix with the big vector 3J coefficients, the square roots in this equation. We have the vector with the big vector 3J symbol we need to calculate. And we have no big vector 3J symbol. Then we have a system with the matrix system to solve. It is still not easy to solve, but we use the LU decomposition to solve the system. And we have 2 techniques inside our code. One for if the system has a solution, and if the system not has a solution, but it forces to have a solution. Those are some techniques of calculating. Then, with this, we talk about the bispectral constraints, because we have a lot of constraints to calculate the bispectrum. The first constraint is the triangle inequality, because the 3-point function is basically stood of triangles. It's the future. Put 3 points in the space, we can create a triangle. So the triangle inequality is one of these constraints of the bispectrum. The second one is the parity invariance. The values of the sum of the multiples in the harmonic circle need to be even. It's second constraint. This is told to us about how many bispectrum we can calculate. Because some bispectrum can be from 0 because of this part of this constraint. Another constraint to make this is the rotation variance. When the sum of the m in the harmonic spherical functions, if the sum of the m's in these values are not 0, the bispectrum is 0. So we need to be this in the sum 0, 2, or we not calculate the bispectrum of the series. Then we need to put these constraints on our model to make the calculation of the bispectrum. But it's not the only piece. But for the case of the bispectrum, I'll talk about how we use this model. To use the model, we need simulations of the sky or maps of the sky or test map field, right, or picture. In our case, for the bingo, we use this type of simulation. We have, for example, the total simulation in this first image, the back, the other image. Then we have the foregrounds, and if we remove the foreground, we have the 21 centimeter simulation or the height simulation. In our case here, we use the flash simulation and the anybody simulation. As Professor Judson talked about later talk. And we have here, for instance, the white noise information and the bingo mask. We need to mask this thing. So we have a map, we have a code, but we need to work in the case we need to study in the bispectrum. Because I can calculate the bispectrum for a lot of types of triangles. But in our case, we choose 3 types of triangles. The types of triangles are, the first one is we call equisize, and each bispectrum case makes some new constraints in the code. For instance, the excise case, we need the sum of the multipoles are the same. We need the same perimeter, the triangle. In our case, we put this perimeter as like 300, and the max multipole we use here is the 300 in this case. For the isosceles case, we have 2 sides of the triangle the same, or the multipole values they are the same, and one value is bigger than the other 2. In this case, we have the one multipole equal to multipole 2, the second map, and the third map is the bigger or equal to the. And the max value of the multipoles in this case is 150 to the multipole. We chose this in this case because the isosceles have a lot of calculation because of this constraint. We have a lot of points of it, and make the codes slowly yet. In the last case is the most simple case, is the equilateral case, when we have the same value to the all multipoles in the elements. And we choose here the 300 value of the maximum multipole. We choose the 300 for the best case because the bingo have idea to study around the 300 or 400 value to the multipole. In the power spectrum case, for instance, and you use the same for the bispectrum. Then, with all this information, we can calculate the bispectrum. Or after make the sum of studs, sum of time the computer make the programmation and the code, we can calculate the bispectrum field. And then are our results. The first results I showed to you are the excited result. For in the first in the top of the slides are the excited for the foregrounds. And as Professor Jadwin said to us, they have the same structure information. If we change the frequency. Each image here are different ratchet, or for our case, different frequencies. And we have the same structure in the foreground case. So these plots are matrix plots of the all spectrum calculations, and we have a mirror image. right side, the middle of the left side. Okay. And then we can see this structure here in these regions of the foreground. Then we can, when we stood the white noise and 21st century simulation, both Sunday, we don't see the same structure and different frequencies, but we see this type of information. So it's these plots are in the forward presented in the list last year. The next slide I show to you results, the new results for the two type of simulations of the 21st century from Flask in the top of the slide and the N-body simulation in the bottom of the slide. And the first we can see is they don't have the same structure in the results because they are from different fonts, different sources, right? In the top side is the Flask simulation, how it goes through how they doing that, how they make that simulation, and the bottom simulation are the N-body simulations talked about by Professor Jeff in the last talk. They are from different sources. They are not the same, but the value are similar. The value of the value spectrum. Okay. The second, the next slide, I'll talk about the isosceles case. The isosceles case is a difficult calculation, as I say, and to see some structure in the results, you need to plot the intensity of the values around to 0.01% of the big value, because the other values are so weak. This, if you like plot 100% of the intensity, we can see nothing in this region. We only see the part of around the 0, and the part in this part here around the 140. And it's very curious when we see this part, and we need to study why this occurs here. Why we have intensity so big in this region. We don't know why. If it's a model problem or if it's a 21st century from 21st century. And to study these cases in the isosceles case. But my work now, the big work now is around the collateral case, because they are simple plot and they are the simple to calculate, they are the fast to calculate, and they are probably the easy to make the statistical analysis, because they are a simple plot. Make a statistical analysis of the two-dimensional plots are a little bit different, but in the one-dimensional plots, easy to do. And then here I show to you two different beams. In this case, the beam 15 and the beam 30 of the simulations from the N-body simulation and the Flask simulation, the first two columns. And in the last column, in the extremity right, we see the comparison between these two spectrum results. And we see here the similar shape of the curve in this case. Okay, then we need to study this statistics about these results, and we start to do in this last semester. And here is the first results for us. We made it using 300 simulations from the one raw simulation, we get the raw simulation. The principal simulation, make another simulation from simulation with the same CL, but using different seeds, and calculate the bispectrum of these maps and make the statistical analysis of this and get this some error bars to plot the dots, the values of the bispectrums beyond error bars. This is the first results. We have some results touching the zero, but some results will have little error bars. And we need to study how if it is occur really, or we need more simulations to make a better error bars. So the last slides are about the next steps. What you need to do first, finish the statistical results, the database. We are using the Samsung supercomputer in Brazil, and we need to. It depends from for your key. Sometimes it's quickly, sometimes not. Then we need to wait some small supercomputer. We need to make the cross check the bispectrum model with the theory. In the first case, in the Anderson study, we need to get the primordial number of series, so the theory of the primordial number of series, and generate a sky map with this theory. But it's not simple because we cannot get, for instance, CLs from the results with the primordial number of series, and use the usual code like how Python generates the map, because they use the idea for all CLs are put in linear Gaussian CLs. And in this case, it's not Gaussian CLs. They have it Gaussian. It's a problem. We need, for instance, use a N-body simulation with the primordial Gaussian inside to generate in the definition one model or map simulation, raw simulation of this type. Right, and it's important step of this study we need to do. The other point is they study formal residuals using the new version of the both codes, the bispectrum codes and the removal foreground model. We need to take the new version of the both and generate simulation and make the removal and study the bispectrum in the stage to see to study the formal residuals in these results. And the last one is use this model in the simulation with the interaction models. We have a students study the interaction models, but it's the same problem as I talk about the second point. We need to get a map with these interactions and not take the CL and use the code generation. We need a raw map simulation from this space too. To do some points, there's 2 points here. I try to go to China in the next year, try to go and make this study with the Professor Alessandro and the Alessandro in China. For 2 months. So that's it. Thank you for inviting for learning about Iowa.
Questions, comments? Why the men be tired? Oh, okay, so let's thank Giordani again. Thank you, Giordani. Okay. So, then we finish all sections of talks and, all, the first part of the big collaboration meeting. So now we,
Tomorrow, 4 p.m.
yes, we see everybody here tomorrow at 4 AM here at UNCG for the trip for a gift. 4.5.
Yeah, exactly where we should get at each place together.
Well, I don't think I just.
Eu vou passar a informação para você.